Hey guys, in this video we're going to be talking about enthalpy. At the end of this video we should be able to use Hess's law to calculate enthalpy changes in a reaction and use standard enthalpies of formation also to calculate our enthalpy of a reaction. Okay, so when we talk about Hess's law, this is when we take a reaction and carry out in a set of steps. So we're carrying out a reaction in a set of steps. And with each step, it's going to be summed up. The different steps can be summed up to give us our overall reaction, and it also will give us our overall enthalpy change. So the sum of the steps gives the overall reaction, and the sum of the enthalpies of the steps gives the overall enthalpy of the reaction. Okay, so remember that enthalpy is independent of numbers of steps or path taken because it is a state function. So enthalpy is a state function, which is why we can do this. Because enthalpy is a state function, all we need to do is find a path to get from our reactant to our product, and that's all that matters. So just need to find a path, any path. Doesn't matter what the path is. Okay? That, however, keep in mind, a note, states are important. You must keep your states in check. You must pay attention to the states of the reactions that you're adding together and make sure that states at the end are correct for your overall reaction. Now, Hess's law, I feel, is much easiest or the easiest to understand by doing an example. So this is an example of a Hess's law problem. We have an overall reaction that we want to find enthalpy for. So this is what we want to find our enthalpy for. Okay, and we have a series of reactions that will in some way combine in order to give us our final overall reaction. So we want to take these three equations right here, combine them in such a way that at the end of it, we have this equation. Some notes about the reaction within Hess's law. If you've got a reaction written in the forward direction and you flip it, you are now looking at the reverse direction of the reaction, and your enthalpy for that reaction will be the reverse sign. So any of these equations that we flip, we're going to change the sign of our enthalpy from a negative to a positive or positive to a negative. Enthalpy is also a term that is extrinsic, so it depends on amount. So anytime we multiply any equation reaction, we're going to multiply our enthalpy as well. Okay? Now, when I solve for Hess's law problems, I find it's best to look and see what I need and what reactions I can get what I need from. So we're going to start out with our carbon solid. This first reaction has carbon solid. In our desired reaction, we have carbon solid reactant. In our series of reactions, we have carbon solid as a reactant. So I feel that I can go ahead and just use this equation as is. So I'm going to go ahead and write it down again. Like so. Exactly as it's written before, because I don't need to do anything. I don't need to manipulate this equation in any way to get it to reflect the equation that I have above. Okay, next I want to look at my water. So I have water in the gaseous state. So if I look, there's only one reaction that gives me water in the gaseous state right here. Now, if I look at my desired equation, the one that I'm trying to combine equations to get, I see that there are only 1 mole. There's only 1 mole of water here, and it's a reactant. Here, I have 2 moles, and it's a product. So what I'm going to need to do to this equation is I'm going to need to flip this equation, which will flip my sign, and I need to divide by 2. So this equation will be flipped and divided by 2. Anything we do to our reaction itself, we're going to do to our enthalpy as well. So I'm going to go ahead and write this out. So divide this whole thing by 2. That gives me 1 water in the gaseous state. Again, paying attention to those states. 1 hydrogen molecule. And a half of an O2 molecule. And that's all right. We can have halves. That doesn't matter. Sorry, just readjusting. Okay, now, like I said, anything that we do to our equation, we have to do the same thing to our enthalpy. So now instead of being a negative 483.6, it's positive, and we're going to divide that 483.6 divided by 2. So it would be positive 483.6 kilojoules divided by 2. So flipping the sign, dividing by 2. In addition to getting that water, I also now have my H2, and it's in the correct place. So we've taken both of those and put them into our equation. The only thing we need left is our carbon monoxide. So carbon monoxide is only in this equation right here. In the desired equation, it's a product and there's 1 mole. In this equation, there's 2 moles and it's a reactant, so we're going to need to do the same thing, flip and divide by 2. Okay, so flipping and dividing by 2 gives us CO2 gas, one of them, 1 molecule of CO gas, and a half a molecule of O2 gas, our delta H. We're going to take the positive 566.0 kilojoules divided by 2. Next, I want to go ahead and combine my equations. So I'm going to look and see what I can cancel out. So anything that's the same on both sides is going to cancel out. Anything that's the same on one side is going to combine. So if we look here, this carbon dioxide is a product. This carbon dioxide is a reactant. 1 and 1, they will cancel out. And then we look. We have this O2 right here as a reactant. A half O2 molecule and a half O2 molecule. 2 halves gives us 1. Those will also cancel out. And then everything that's left is what's in our equation. We have carbon solid, water vapor, going to hydrogen gas, and carbon monoxide gas. And when we combine our delta H's, we get a delta H of reaction of 131.3 kilojoules. This equation matches this equation, so we have done this correctly. And we've solved for our enthalpy of this reaction by combining other reactions and their enthalpies. We have something that's specifically called enthalpy of formation. So the enthalpy of formation, given as delta H, not of formation. So this F is formation. This not right here means we're under standard conditions. Where standard conditions are 25 degrees Celsius and 1 atmosphere. And anytime you're giving those standard conditions, it's just to make sure that everything was gotten in the same exact manner, so that there are no additional variables to take into account, like different temperatures. Okay, so when we're talking about the enthalpy of formation, we're talking about the formation energy of a compound. So energy to form a compound from its elemental components. Okay? So we're taking elements, we're combining them to form a compound. For instance, let's take methanol. Ethanol. Ethanol has carbon, hydrogen, and oxygen. So the elemental form of carbon is carbon solid. The elemental form of hydrogen is hydrogen gas. And the elemental form of oxygen is oxygen gas. So our elements are going to combine to give us ethanol. So we take our carbon solid plus our hydrogen gas plus our oxygen gas combines to form our ethanol. Now, as a note, we want to go ahead and balance this, but in a formation, we always want to keep this as 1 mole. So we're forming 1 mole of product. Okay? So there are 2 carbon atoms in our product. We need to put a 2 here. There are 6 hydrogen, 3 here, and 1 oxygen. So to get to 1 from 2, we need to divide by 2. So we're basically going to multiply this by 1/2. Okay? And this gives us our formation equation. And these formations are given in a table. And I will give you guys these tables. But it's delta H information. This value right here is what's given. And it's negative 277.7 kilojoules per 1 mole of ethanol. Okay, pretty simple. We can use these standard enthalpies of formation, what I've just written here, in order to solve for Hess's law problems. So that's why they're really important. But they're going to come in a table that looks something like this. So this is probably the table that I'll provide for you guys on D2L. But these compounds, every single one of them will have an energy that's required to go from the elemental form into the compound form. Okay? And just while you're making them, when you're making these equations, just keep in mind that you should be able to find all of your elemental forms by looking on your periodic table. So your periodic table, it'll show you what states generally. So carbon's a solid, hydrogen's a gas, oxygen's a gas, iodine is a solid. Just keep in mind our diatomics, so the ones that you guys should have committed to memory. So you've got hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. So those 7 are all diatomics, and that's diatomics. The elemental forms are diatomics. So when you use those in standard enthalpies of formation, make sure that you use the diatomics there. Okay, so when we take this and we solve for a Hess's law type problem using enthalpies of formation, we are going to take and basically break apart an equation. Anything that's in a compound form, if we're using standard enthalpies of formation, we're going to take those compound forms and make them using standard enthalpies of formation. Let me show you what I mean. So let's actually take that same equation we had just above. We've got C3H8 reacting with oxygen gas to produce carbon dioxide and water. Okay, so this is just a typical combustion reaction. But we want to solve for the enthalpy of this combustion reaction. So our delta H of combustion using standard enthalpies of formation. So this is going to be at the end a standard state because we're using standard enthalpies of formation. So we want to solve for that standard enthalpy of combustion. So anything that's in a compound form, you're going to write out standard enthalpy of formation equations for. So we're going to want to solve for C3H8. We're going to solve for CO2. and H2O. Our C3H8 is in the gaseous form. Carbon dioxide is in the gaseous form as well. And then water is in the liquid form. So when we use this table right here, make sure you note what states of matter you have, because our liquid form of water has a very different enthalpy information from our gaseous form of water. Okay, so for propane, we have 3 carbons and 8 hydrogens. So we're going to take carbon solid plus hydrogen gas, and that will form our C3H8. And we'll just put a 3 here and a 4 here to balance it out. Do the same thing for our carbon dioxide. We have carbon and oxygen. So we have carbon solid plus oxygen gas. And there's 1 carbon, 2 oxygens on both sides, so we're good. And then our H2O, H2 gas plus O2 gas. Our hydrogens are already good. We have 2 on the left side, 2 on the right. We just need to put a 1/2 in front of our oxygen to take it from 2 to 1. So we're basically dividing that 2 by that 2 to give us 1. And then these are all going to be in a table. And from the table, we can get these formation values. And they're going to be for propane, negative 103.85 kilojoules per mole. For our carbon dioxide, negative 393.5 kilojoules per mole. And then for our liquid water, negative 285.8 kilojoules per mole. Now, at this point, we go back to the same exact type of Hess's law problem that we had just a minute ago, where we're going to take and manipulate each of these equations in order to get our desired equation. I'm just going to make myself a little bit more room. Okay, now we're just going to match everything up. First, we want our propane. So this is as a reactant. This is as a product. So we're just going to flip it. We don't need to do anything else to it. So we have C3H8 gas goes to 3C solid plus 4H2 gas. That has a delta H of 103.85 kilojoules per mole. It is no longer a formation because we flipped it, so we're just going to keep it as a delta H naught. Next, don't even pay attention to any of your elemental forms here. They will balance themselves out. We're just going to look for our next compound. So our next compound, 3 carbon dioxide molecules. Here are our carbon dioxide molecules. They are as products, but we need 3 of them, so we just need to multiply this by 3. No, we flipped this one. So multiply this by 3. This gives us 3C solid plus 3O2 goes to 3CO2 gas. And our delta H naught is equal to negative 393.5 kilojoules per mole times by 3. And then our last one, we're going to take our water, solve for our waters. There are 4 here, 1 here. We just need to multiply this by 4. This gives us 4 H2 molecules, 2 O2 molecules. 4 times 1/2 gives us 2. And 4 H2O molecules in the liquid state. Our delta H naught here is negative 285.8 kilojoules per mole times by 4. And let's see how this works out. So again, we're going to cancel out anything that's the same on both sides. We have There are 3 carbon solids here, 3 carbon solids here. They will cancel out. And then, let's see, 4 H2 molecules here, 4 H2 molecules here. They will cancel out. And then nothing else is on opposite sides of the reaction, so we can go ahead and combine C3H8 gas plus 3 plus 2 gives us 5 O2 gas. And as I said, here it is. Didn't need to worry about the O2. And then we get 3 CO2 gas plus 4 H2O liquid. And that is the equation here. Then solving for our delta H of combustion, it's going to give us negative 2219.9 kilojoules per mole of our propane, or per reaction. Okay, we can write it either way. The last thing I want to talk about quickly is the idea of energy in food. For the most part, probably the energy that you guys are familiar with is energy in food in the form of kilocalories, right? So when food is metabolized, it produces energy. And that value, that calories, is determined using bomb calorimetry. The energy itself specifically comes from the metabolism of macromolecules. And our macromolecules are going to be proteins, carbohydrates, and fats. Okay? So, fats are going to have 9 kilocalories of energy per gram. Carbohydrates and proteins have 4 kilocalories per gram. Okay? So we could actually determine from just our fats, carbs, and proteins how much energy we can get by eating something. Probably some other energy sources you're familiar with is energy and fuel. So different fuels will have different fuel values, so kilojoules per gram. And one of the reasons why hydrogen fuel is such an exciting prospect is because of the significant fuel value that it would produce, and the fact that if you combust hydrogen with oxygen, you produce water. Right? See, the only byproduct from the combustion of hydrogen is water. So wouldn't that be just swell if we could do that? Anyways, but those different fuel values will determine how energy efficient it is to combust these different types of fuel. There are different sources of energy within the US that we use. The most common is petroleum-based, but natural gas is up there. Coal, unfortunately, is up there. Nuclear, so remember our nuclear chapter talking about all the energy you can get from there. And then, sadly, renewable energy is way down there. Okay, but that's everything for our energy chapter or energy unit. I will hopefully talk to you guys in the next one. Bye, guys.